This is some uranium metal. This is its atom, this is the nucleus of that atom, and it is made of positive protons and neutral neutrons. They both have a mass of 167 septillionths of a gram, which is really small, so we call it an atomic mass unit. The number of protons in a nucleus tells you the elemental identity, and the number of neutrons plus the protons tells you the mass of that atom in atomic mass units. When two nuclei of the same element have different atomic masses, they are isotopes of each other with different properties. Uranium-235 and uranium-238 are both uranium, but they are different types of uranium that express different properties. Different isotopes have different stabilities dependent on the tug of war between the strong nuclear force and electromagnetism. Electromagnetism causes proton-proton repulsion because of their common charge. It has a theoretically infinite range, but it is relatively weak compared to the strong force. Nuclear strong force is roughly 100 times stronger, but loses its strength at only 3 femtometers. If the nuclear force is stronger, the atom holds together. But if the nuclei becomes too massive and the nuclear force gets stretched too thin, the electromagnetism causes a release of energy and particles to get back to stability. This state of passive energy and particle release is called radioactivity. This process takes a lot of time, however, and a single nucleus releasing its binding energy isn't that exciting. Luckily, some German radiochemists named Otto Hahn and Fritz Strassmann discovered that if you bombarded a radioactive nucleus with more neutrons, you can cause the nucleus to split into 2 smaller nuclei with 1 or maybe a couple neutrons left over. Those neutrons can then carry their momentum to a neighboring nucleus and do the same thing, creating a chain reaction releasing individually small but cumulatively massive amounts of energy, equivalent to the sum total mass of fission nuclei times the speed of light squared. This process is called nuclear fission. This energy most commonly takes the form of heat, and if you absorb that heat in a giant pool of water, it will create massive amounts of steam, and if you run that steam through a turbine, it generates electricity. With AI assistants seeing more use than ever before, there is a massive energy demand that seems to only be getting bigger. I'm here to tell you that a highly efficient and safe solution to a potential energy crisis has been right in front of us for decades now. It's nuclear energy, and it is the future.